Okay, we can go ahead and start today. So today we're talking about what I call Wi-Fi 101. So this is basically looking at, what makes Wi-Fi work, how does it function, all the sort of basic stuff that goes into it. Um, for the simple reason that Wi-Fi can be really complicated, right? You're dealing with something that is playing around in an environment where you really can't see what's going on. We've got limited tools to understand what's going on. So I just want to go through here today, sort of explain Wi-Fi, how it works, why it works the way it does. And then towards the end here, we'll give you some best practices on how, the best ways that you should handle certain situations. We'll go ahead and start here with the first slide. This is just one slide, just a little background on who Zyxel is. So Zyxel has been making computer networking equipment for over 30 years. We got our start all the way back in 1989. We are a global company. We serve 150 different global markets. Our company's main headquarters is in Hsinchu, Taiwan. Our North American headquarters is based out of Anaheim, California, so just down the road from Disneyland. That's our offices. So it's got our warehouse there. It's got our sales team there. It's got our tech support team there. Everything's based out of our Anaheim office. So now let's get started talking about Wi-Fi. So I want to start here with just a little bit of a timeline here, just how long and how far Wi-Fi's been around for us. So the official 802.11 standard got ratified all the way back in 1997. So for a lot of people, they think Wi-Fi started with 802.11a and B. But in reality, there actually before that were 802.11 products. In fact, when I started at Zyxel, back at the dawn of time, we actually still had some 802.11, no A, no B, products in our warehouse that were still sticking around in our warehouse there for us. So Zyxel's been part of Wi-Fi for quite a long time. 802.11a and B, which are the ones you're probably most familiar with, the standard was ratified in 1999. Then 2003 gave us 802.11g, 2009 for 11n, and then 2013 gave us 802.11ac. And then we had a huge gap here between 11ac and 802.11ax, more commonly referred to as Wi-Fi 6. And right now, the standard for Wi-Fi 7 is expected to be out in 2024. So you can see as time went on, the gaps between the different versions of Wi-Fi got longer and longer, and now they've compressed again with the differences here between 802.11ax and 802.11be or Wi-Fi 6 and Wi-Fi 7. I will say here before we go on, you can expect to see products claiming Wi-Fi 7 before the Wi-Fi 7 spec gets certified. We have seen this over and over again in the Wi-Fi space. Probably the first really prominent time it happened was with 802.11n. We had a number of products on the market that marketed themselves as pre-N. And many of them promised that you would be able to upgrade to the full 11n standard by a firmware update, which never came because between the people launching their pre-N products and the actual ratification of the standard, enough had changed with that standard that some features just couldn't be supported. They needed to be baked into the chips and they were not. Then we saw something similar with 802.11ac. You saw some products hitting the market early. You officially saw 802.11ac products marketed as Wave 1 and Wave 2. And that was just because, again, products got out to the market early, didn't have all the features. And then the Wave 2 came along, which was chipsets that supported the full spec. And we saw something similar with Wi-Fi 6, only with Wi-Fi 6, there is no Wave 1 or Wave 2 or pre versus full. People are just calling things Wi-Fi 6. That were missing and are still missing some of the key features that are part of that standard. So that's just something to keep in mind. And we'll probably see something similar with Wi-Fi 7, where there will be products hitting the market early, and those early products will likely be missing some features that end up as part of the final spec that gets ratified in 2024 or whenever it happens to take place. These timelines have a tendency to get pushed back. It takes a while for the final certification and ratification to take place. So let's talk about some of the players here in the Wi-Fi space. The main one here is the IEEE. So they're the ones that create those 802.11 standards. In fact, that's what the 802.11b or AX or AC, that is referencing an IEEE standard that has been certified, ratified, and published. So that's what everyone is supposed to be following and enforcing. So one of the problems that we ran into back in the early days of Wi-Fi is that not everybody's 802.11 product was compatible with everybody else's. In theory, they were following the same spec, but there's always room when it comes to interpreting the English language or whatever language you're looking at. There's always ways of interpreting it differently and things that maybe were left a little too loose that should have been more specific, which can cause issues. And then, of course, there's just people taking shortcuts and not bothering to make sure they're following all the rules. So that was causing issues and problems with adoption because you didn't know that your Zyxel equipment would necessarily work with your Cisco equipment. So that's where the Wi-Fi Alliance got started. So the Wi-Fi Alliance is an industry group that was founded primarily by the sellers of Wi-Fi products. And the idea here was to solve some of these incompatibility issues and be able to certify products are compatible with each other. Um, so that's why you will see the Wi-Fi logo on products. These days, things are generally pretty good as far as compatibility goes. So generally, you only see this Wi-Fi certified logo on consumer products. You generally don't see it very often on business class products. So one thing that's kind of interesting is, some of these Wi-Fi 6 features we're only actually required to, in order to get Wi-Fi 6 certified by the Wi-Fi Alliance, um, last year in 2022, even though the standard had been out and products had been on the market for a long time before that. So just something else to goes in there to show you that, some of these features that are part of the IEEE standard may not end up in the final product. And even in this case, where the Wi-Fi Alliance is certifying product, they're determining which features need to be there and which don't. And they do change that as time goes on, allowing the older products to remain certified as a grandfather status. The Wi-Fi Alliance is also a marketing group, and they're the ones who decided to change from calling products 11B and 11AC and 11AX to Wi-Fi 6, Wi-Fi 5, Wi-Fi 4. So they're the ones who've come up with that, and they're the ones that have really pitched it, which is really taken on here with Wi-Fi 6. The other group here to talk about is the FCC, the US federal government. They are the ones who set the rules as far as what RF frequencies we can use, how much power output we can use, et cetera, et cetera. So in order to bring in a product here to North America, you have to do your own self-certification. So you're required to hire a third-party lab, have them perform certain tests, and then you have to submit that to the FCC where it is published for everyone to see. And the FCC is highly influential. Many other countries out there simply follow the FCC requirements, or their own requirements are basically based off the FCC rules. So those are the three main guys you'll see names come up when we're talking about Wi-Fi, and that's the role all three of them have. So just again, really quick, IEEE sets the official standard. The Wi-Fi Alliance handles marketing and certifying compatibility between products. FCC sets rules as far as frequencies and power utilization of the different products. So now let's start talking a little bit more about how Wi-Fi itself works. So Wi-Fi works using radio waves. And radio waves are in general pretty much the same thing regardless of what we're talking about. So things you see with television transmissions, radio transmissions, walkie-talkies, they're all using different chunks of the wireless spectrum. They're all radio waves, so they all follow some of the same general rules. So if you're already familiar with some of these other technologies, most of that will carry over into Wi-Fi and how it works. So just as a general rule, as frequency goes up, the easier it is to encode more data onto it. That's one of the reasons why 802.11a was faster than 802.11b. A operated on the 5 gigahertz spectrum, 11b operated on the 2.4 gigahertz spectrum. But as frequency goes up, the lower your range is. So that's something that you have to keep in mind, especially now with Wi-Fi 6E and 6 gigahertz. 6 gigahertz is significantly higher frequency than 2.4 gigahertz, and you will see the range being significantly reduced for your Wi-Fi 6 products, or your Wi-Fi 6 clients versus your 2.4 clients, even if they're both connecting to the same access point. So the radio frequencies that we get to use is regulated by the FCC. And in general, when you want to broadcast radio transmissions, you are required to get a license from the FCC. For those of you that do outdoor point-to-point links and things like that, you're probably very familiar with that. So what the FCC has done over time is they've opened up small chunks of spectrum that anybody can use as long as you comply with their rules. So that started off with the 900 megahertz frequencies. There's also some smaller ones there. I think, like remotes for garages and stuff like that operates different ones. But in general, the main ones that we deal with in the consumer space are the 900 megahertz frequency, the 2.4 spectrum there, and the 5 gigahertz. So these are areas where you can operate without needing to license to broadcast things. So you'll notice this is not specifically for Wi-Fi, the 2.4 and 5. This is just the section that we use. So that means that this chunk of spectrum, your Wi-Fi devices are sharing it with other wireless devices that want to operate in these spaces. And we will talk a little bit more about 6 gigahertz here towards the end. So another thing here, when it comes to radio waves, is generally the way you measure it is in dBm, decibel milliwatts. So for every 3 dm of power increase, or excuse me, every 3 dBm increase in the rating on your product is essentially a doubling of the power. So 23 dBm is double the power of 20 dBm. So what you will look at when you look at products is generally when you're looking at the spec sheet, particularly on business class products, you will see dBm used for your power output. You will see dBi used for your antenna gain. And this is really handy. So when you're doing calculations, especially in the old days where you used to provide your own antennas and your own cabling, which most people don't do now unless you're doing some sort of outdoor deployments, is you can take and very easily add and subtract dBm and dBi together to get your total output power. So you could subtract out cable loss and connector loss. You can easily add in your antenna gain and amplifier gains and get the total radiated output power coming from your product. It just all adds and subtracts together and gets you your final number. When you look at consumer products, those were generally advertised using milliwatts instead of dBm. So why did they do that? Because it exaggerates the differences in spec, right? So you would see, for those of you that are old like me, you might remember when people would advertise 200 milliwatt, output power of your router as it being a really big boost. And why did they do that? Because most other vendors were at 20 dBm or 100 milliwatt. So by going from 20 to 23 dBm, you increased your milliwatts from 100 to 200. So it sounds like a much bigger, improvement than saying, hey, ours is 23 dm, our competitors are at 20. And of course, these days, most products default to at least 23 and often more power coming out of them. However, this going from 100 to 200 also creates the impression that you are doubling your range, which you are not. Signal drops off quite dramatically. So the boost you see from 200 to from 100 to 200 is actually much less than you would think just seeing the raw number there in milliwatt. So some other things that people tend to overlook that are really, really important, and probably the most important one is your signal to noise ratio. This is going to be key in determining how good the quality of Wi-Fi connection is and really determining the speed of your wireless connection. And this is just a measure of the signal, right? That signal that you're wanting to hear coming from your access point versus the level of RF noise. Things being broadcast by other wireless devices in the vicinity, including other access points that may be operating on the same channel. So the better your signal to noise ratio, the more solid the connection is, the more data that can be sent, the faster that connection is going to be for you. Another common term here is attenuation. So attenuation is just how much signal degrades. So as the signal radiates out from its source, the signal does drop off. So it drops off much faster as it passes through solid objects or more dense objects. So going through open air can travel very far. Inside a building where there are walls and people and equipment and machines, it's going to drop off much faster. So if you ever wanted to know, hey, what is my range? What can I do here? This is the formula that you need to use to calculate it. So it's not an easy thing. There are calculators on the internet you can use where you can just punch in these numbers. You tell it the output power of your device as you found on the data sheet. You tell it the frequency you're using, and it will be able to calculate and tell you how far you can send that signal. And here's just a list of some common things out there. Anonymous attendee is asking about Wi-Fi channels. So I've got a slide coming up in a little bit here where we'll talk a little bit more about those Wi-Fi channels. And if that doesn't cover what you're asking about, go ahead and send that question in again. Anyway, so this is just some common listings here of common building materials that you're going to run across and how it affects the attenuation of the signal. So a window going through just a simple glass window can cause 3 dB of loss. However, if it's a tinted window, it can be up to an 8 dB loss, right? So one of the ways that the tint windows is they add a metallic coating on there to reflect infrared back out, as well as visible light. So that metal blocks that signal a lot more than just glass alone does. A window screen also is really good at blocking signal. And then just when you come to walls, obviously, the denser the material is in the wall and the thicker that wall is, the more the signal is going to be degraded. So when it comes to Wi-Fi range, right, it's a combination of, how strong that signal is, what the signal to noise ratio is, the attenuation in your environment, the frequency being used. You have to combine all those together to figure out your range. But one thing people tend to forget and overlook is that Wi-Fi is two-way communications. Your client device needs to be able to hear your access point, but your access point also needs to be able to hear your client device. And people tend to overlook that. And there are generally huge differences in power output between your access point and your little mobile device. So, it's very common for a business class access point to have total output power of around 500 milliwatts, whereas it's very normal for a phone or tablet to have output power of 25 milliwatts or less. So that causes a problem that we see all the time and confuses people a lot, which is you've got your phone. It shows you've got a three bars of Wi-Fi signal, and yet your internet connection isn't working. Now, the reason for that is because your phone is telling you how strong the signal is from your AP. It's hearing that signal nice and strong, and it's telling you that. It isn't telling you whether or not your AP can hear the signal coming back from your mobile device. So that's why you run into those scenarios where your phone thinks you've got a working Wi-Fi connection, but it either doesn't work at all or it's horrible as far as using it goes. And it's because you're actually out of range of the AP for your client device. And that causes issues when it comes to roaming sometimes, where your client device, won't roam because it thinks the signal it's getting is still good enough, but the AP isn't able to hear it. So that's why one of the settings we have in our Wi-Fi settings on our access points is we do have the ability to set a minimum signal strength for a connected device. And if a connected device drops or the AP, the signal strength coming from that client device gets below that cutoff, the AP will disconnect that user, hopefully allowing that device to then be able to reconnect to another AP in the area with a stronger signal. So when it comes to radio waves, they have a lot of different behaviors, and most of these behaviors are the same or at least very similar to the waves that you would see in water in, say, a pond or a tub or something like that. So when you throw a rock into a pond, the waves radiate out in a circular pattern, and it's roughly the same thing with Wi-Fi. The signal radiates out, and as it does, it interacts with its environment. So it can go off in one direction, it can hit something, and then the waves will reflect off of it. So you see that with water all the time. Another thing that can happen with Wi-Fi waves is they hit a solid object and they can actually sort of wrap around the outside of the object, changing its trajectory as it wraps around. And that again is something you can see with water waves. And then depending on the shape of the objects being hit, you can diffuse or scatter those waves so they go off smaller waves in different directions. Now, one thing we can do with Wi-Fi that we can't, that you don't see with water, is the signal does have the ability to pass through solid objects. It just loses its strength, right? So these are all sort of things that are going on in that RF environment, and unfortunately, we can't see it. So it's often the cause of problems that you run into in Wi-Fi. Is you may have good signal strength, but because of what's going on with the signal bouncing off of things, it can sometimes cause issues with reception. And we're going to come back to this here in just a couple slides. One more thing to talk about with Wi-Fi behavior. In general, with Wi-Fi, each device has to take a turn broadcasting. If two or more devices broadcast at the same time, you run into interference and it causes the packets to be dropped. This is similar if any of you have been on a long road trip, you're listening to a certain radio station, and you get to that point out there, particularly at night, where your radio is picking up the radio station you're listening to, but it's also picking up another radio station using that same channel or a nearby channel, right? You might be listening to 101.1. This one may be broadcasting on 101.5. And it's close enough together that your radio now is picking them both up at the same time, and it just turns into a horrible mess. And that's the same thing that happens with Wi-Fi when you've got two devices broadcasting at the same time. So basically, all the way back in 1997 with that first 802.11 spec, this is how they decided to solve it. Basically, the way it works is your device, when it has something to send, it senses the medium. So that just basically means it listens for a split second to see, hey, is anybody else broadcasting? If nobody else is broadcasting, it uses a random number generator to decide how long to wait before repeating the process. If it doesn't hear anybody broadcasting, it transmits. And if somebody else decides to transmit at the same time, you end up with a collision. And you basically have to, both people lose their signal and you get to broadcast it again. So this has remained pretty much unchanged all the way until Wi-Fi 6. So 11N, 11AC, all of these products are still using this same basic flow chart for determining whose turn it is, to broadcast. So one of the challenges you run into, right, is, the Wi-Fi environment and what people are trying to do with it has changed dramatically from what they were thinking about all the way back in 1997, right? So you've now got a lot more continuous transmissions as people are streaming videos and audio. You've got people using a lot more bandwidth than they used to run into, and you've got a lot more wireless devices than anyone ever imagined. So one of the problems you run into, right, is as you add more and more users, you increase the likelihood that two or more devices are going to sense the medium at the same time, see no one broadcasting, and decide to transmit at the same time. So the more often that happens, the lower your Wi-Fi connection quality is going to be. The other problem you tend to run into in this is that it has to do with the receiving range of these different devices. So in this case, we've got two different Wi-Fi devices. They're both within range of this access point right here. And the problem you run into, though, is these client devices can easily transmit to the access point, and they can see the access point when they sense that medium, but they aren't within range of each other. So neither of them can see when the other one is broadcasting, but the access point can hear them both. So if they both broadcast at the same time, it causes interference in those connections to be dropped. So another thing I want to talk about here is data rate versus throughput. And these terms have many different meanings. This is just how I am using them and how I see them most commonly used out there. So when you look at a 802.11 spec, you look at a data sheet, you look at a product listing on Amazon, the speeds you will see quoted are the data rate. So this is the max speed of data or max amount of data that can be transmitted between the access point and the client device. You may also see it referenced in tools and things as the physical rate or the link rate. And this includes all data that is being transmitted. What you see people test with something like, speedtest.net/Ookla or some other tool doing an FTP transfer and timing it, is they are testing throughput. So this again is a measurement of the transmission of data between 2 points over the Wi-Fi network, but it's only including the data that you are actually trying to send. So for instance, if you are downloading a 1 gig file over FTP and timing it, it's only basically measuring that 1 gig of data that's coming from the server onto your client device. It does not include any of the protocol overhead that goes into making Wi-Fi work. And that's a problem for us because Wi-Fi has a ton of overhead that allows Wi-Fi to work, right? We're using these public airwaves that have to be shared amongst a lot of different devices. There's a lot of different forms of interference, both from other devices that are using this space, but also from industrial equipment and electronics that may also be putting out RF noise. So in order for this to work really well, there's a lot of overhead that goes into, checking the data sent is actually what the data received is, scheduling whose turn it is to talk, things like that. So what happens is something like an Ethernet connection, there's very little difference between throughput and data rate because there's really nothing special that goes on over the Ethernet cable to make it work. There's very little going on there. But with Wi-Fi, there's all this extra stuff going on. So because of this, depending on the Wi-Fi standard and how good your RF environment is, there may be up to a 60% difference of throughput versus your data rate, because the data rate's including all that extra data that has to be sent to make Wi-Fi work, where throughput does not. So that's why if you go to Amazon, you look at the reviews, doesn't matter whose product you're looking at, there will be people complaining, hey, I did a speed test and I'm only getting half the speed of what you're calling it. Why are you calling it AX 1800 when I'm only getting 900 megs throughput? And this is one of the reasons why. There are other reasons, such as the wireless client doesn't support the maximum speed that the router does, issues with signal strength, right? Signal to noise ratio. If you've got a poor signal to noise ratio, your connection will slow down, things like that. But this is a very common thing which causes confusion for people. And even with Wi-Fi 6, it's still somewhere in the neighborhood of 40 to 60% overhead to make Wi-Fi work versus the data that you're actually trying to send. So now let's talk about how do we increase speed. Now this is coming at this not from you out in the field. This is how does we as a manufacturer, how does we as a technology company, how do you increase the speed when it comes to Wi-Fi? So one of the main ways of doing this is increasing the encoding, basically how much data can be crammed into a set amount of bandwidth. So 11N products use 64 QAM, 11AC gave us 256 QAM, and with Wi-Fi 6 now, we have up to 1,024 QAM. So that's one way you can increase speed, is by increasing the encoding. The challenges with this, obviously, is in order to encode this data, you need a stronger processor that's able to encrypt the data or compress the data and encode it for you. So it's been one of those things where it's been held back by the technology, right? We're talking mobile devices. So you need something that's got a lot of power, but also doesn't draw, needs a lot of, horsepower, processing power, but doesn't draw a lot of electrical power. So it runs down your batteries. So that's something that's just been, technologically constrained. As chips improve, we've been able to improve this. The next one is increasing the number of spatial streams, and we'll explain what those are in a coming slide here. And the other way you do that is increasing bandwidth. So 11G used 20 megahertz Wi-Fi channels. 11N introduced the ability to use 40 megahertz channels. And 11AC gave us originally 80 megahertz channels, and then the Wave 2 products gave us 160 megahertz channels that we could use. So we're going to start first by looking at the channels and the bandwidth. So anonymous person, this is where I think I'm going to answer your questions. If I don't, go ahead and send in a more specific question. So when we look at Wi-Fi in the 2.4 gigahertz space, if you pull up any sort of Wi-Fi devices, 2.4 channels, you will see that there are 11 channels we are allowed to use. In Europe and some other countries, there may be up to 13 channels, and there are some countries that have even less than us. But 11 is what we generally have. The problem is again, we're using these Wi-Fi channels. So a Wi-Fi channel is roughly 20 megahertz in size. The problem we run into here is that these channels are nowhere near that. They're only about 5 megahertz difference in size from each other as far as the increments go. So what happens is you end up with these 20 megahertz channels overlapping their neighbors. So you see here, if you are using channel 6, you will be overlapping channels 4 through 8. So if somebody else is using channel 3, they are also going to be overlapping 4 and 5. So your channel 6 product is going to be overlapping your channel 3 product or device, and you will get interference in this overlap areas. Again, each device needs to broadcast it by itself. You can't both broadcast at the same time or you run into interference issues, ignoring MUMIMA, which we'll talk about later. But in general, this is how it works. So what that means is realistically, you've only got about 3 non-overlapping channels that you can use in the 2.4 gigahertz space before you start running into interference issues between your different devices. So with 11N, right, we added 40 megahertz channels, right? We're doubling the bandwidth available, which roughly doubles the speed we're able to achieve. The problem you run into with this is, again, there's only about 60 megahertz of spectrum available in the 2.4 gigahertz space. So as soon as you add a second device that uses 40 megahertz channels, you are going to have some significant overlap and interference issues. So because of this, most of your 11N product and everything since then generally has an auto setting where it drops from 40 to 20 when it detects this interference from neighbors. So what happens in the real world is you will set your device to use 40 megahertz channels, but you will end up only operating at 20 megahertz most of the time due to interference issues. So that right there then halves your available, in theory, speeds that you can achieve. So because of this and how little 2.4 spectrum is available is why there was a big push to using 5 gigahertz for doing Wi-Fi, right? So with, excuse me, 2.4, we only had 3 available non-overlapping channels. With 5 gigahertz, we've got like 25 or 26 non-overlapping 20 megahertz channels. So this is why there was a big push starting with 11N to move people over to 5 gigahertz. And this is why we started to see dual radio access points and routers start to become much, much more common. 2.4 for those legacy devices, 5 gigahertz for everybody else. Obviously, one of the other challenges we ran into in this space was range. Your 5 gigahertz radio doesn't cover as much ground as your 2.4 does. So, you couldn't just necessarily swap out your 2.4 APs for 5 gigahertz. You needed to readjust their placement for maximum coverage in the 5 gigahertz space. Now, when you look at this chart, it looks great, right? You've got these, 20 plus channels that you can use. It's wonderful for us. But you'll notice here, the big chunk of this middle spectrum is called DFS channels. And we need to talk about that because this takes away in the real world a lot of channels that we can use. So here's the trick with 5 gigahertz. 5 gigahertz was already in use by licensed operators, people that had to have a license. And the FCC said, hey, you know what? We're going to make this available for everybody who doesn't have a license. And the people that already were using that spectrum said, hey, wait a minute, we don't want these Wi-Fi devices and other devices, non-licensed devices, interfering with our existing stuff. We've been using this for years and years and years. We pay for an annual license. So the FCC came up with rules for how to solve it. Now, one of the most common uses in this 5 gigahertz license space had been radars, both your weather radars, your airport radars, things like that, right? These are really important radar systems that you don't want to interfere with. So the FCC designated these channels that overlap with this existing usage scenario, and put in rules in place on how to use them. So for a unlicensed user, before you can broadcast on a 5 gigahertz DFS channel, you have to make sure nobody else is currently using that channel. No legacy users are currently using that channel, and then you can start broadcasting. In addition, if you ever detect another legacy user using that spectrum, you have to stop broadcasting immediately and change to another channel. So if you are changing to another DFS channel, you will need to pause and wait to make sure that that other channel is not being used by a legacy user, and then you can start broadcasting on it. So one of the challenges you run into is if you're using these DFS channels is your users may periodically be disconnected due to legacy users using that chunk of spectrum that you were using, or just some sort of RF interference coming from an industrial equipment that might get mistaken for a legacy user. So users might get kicked off, and if you're having your AP automatically switch to a different DFS channel, it's going to introduce some additional gaps. Well, they check that channel before starting to broadcast on it. So you may get user complaints. The other problem you run into here is getting certified to use these DFS channels. It can take up an extra 6 months versus regular FCC certification. There's extra steps you have to go to and things you have to do to prove your product is complying with these DFS rules. So because of that, and it's particularly in the consumer space where everybody's rushing to market to get their product there first, and where most home users don't know what a firmware update is, let alone how to do one, for those reasons, a lot of consumer product doesn't support those DFS channels. So if you have a situation where you have users bringing their own device, they may be bringing devices in that don't support those DFS channels. So just a couple examples from real world, one of which just hit one of our customers last week. We had a customer providing Wi-Fi services, and their users are using Roku sticks to be able to provide IPTV services to those users. And those Roku sticks don't support DFS channels. And by default, or they had set the network to be able to use the whole 5 gigahertz spectrum. So what happened is those users were not able to connect to the 5 gigahertz radio because that radio was using a DFS channel, forcing all of those Roku users over to a 2.4 gigahertz radio, overwhelming the 2.4 gigahertz radio, right? Didn't have enough speed to handle all of the users trying to stream HD video at the same time and overwhelmed the available 2.4 spectrum. Another common one we run into is Apple products. I apologize, I don't know which specific Apple products are, but apparently a number of Apple phones and tablets do not support at least some of the DFS channels. I think it is the Uni 2 area there. So again, if you have your radios set to use DFS channels, those users aren't going to be able to connect to that 5 gigahertz radio. This is also something we get calls a lot of times in. We'll have people say, hey, your access points aren't compatible with Bob's Lenovo, whatever, at laptop. Because when he goes in the conference room, he can't make any connection. And generally what we see is they're using DFS channels, and Bob's Lenovo doesn't support DFS. So for that reason and those disconnection reasons, a lot of you will choose not to use these DFS channels. So that drops us from 26 non-overlapping channels down to 9, which still seems like a lot, but certainly much less than we thought we had to play with to begin with. But you remember the reason we're talking about this is because we're talking about increasing bandwidth. So one of the ways we increase speed is we increase the bandwidth. So we go up to 40 megahertz channels versus 20. So now if you're avoiding DFS, you've only got 4 non-overlapping channels that you can use before you start running into interference issues. So again, not a big deal if you're living in a house and this is your home Wi-Fi, but if you're providing access into an office building where you've got multiple APs, particularly an office building that's shared with other users or other companies, upstairs and downstairs below your guy, so you have to deal with, not only your Wi-Fi equipment that you're managing, but the Wi-Fi equipment that they're using. Also can cause issues in condos and apartments where you've got a lot of people crammed in together, and those walls tend to be awful thin, so signals can go through multiple units and cause interference quite a long ways from where they're necessarily broadcasting from. But again, we're going for speed. So what do? Well, let's double the speed, right? So let's double the speed here from 11N40. Let's go up to 11AC and use 80 megahertz channels. So now you're stuck just with 2 non-overlapping channels. So as soon as you have 3 access points in the area, you're going to either have interference or you're going to need to drop them back down to 40 megahertz channels to avoid that overlap. But if you drop from 80 to 40, you're essentially halving your available maximum speed. And then wave 2 in Wi-Fi 6 uses 160 megahertz channels. So if you want to use those 160 megahertz channels so you can achieve those speeds advertised on the data sheet or on the Amazon listing, they have to overlap with DFS. So what we see here is there's a lot of consumer product that just doesn't support 160 megahertz. In fact, there's a lot of access points, including some of ours, that we haven't implemented 160 megahertz on because it requires DFS and because there's so few people in the business realm that are going to choose 160 megahertz over dealing with DFS. And that changes with Wi-Fi 6E. And again, we'll talk about Wi-Fi 6E later. It's just because a lot of Wi-Fi 6 and 6E has changed things a lot. So it's better to talk about them separately. So one of the other things we talked about here is spatial streams. And this is going to be sort of a callback to the slide earlier talking about how Wi-Fi waves behave in the actual environment. So as mentioned before, Wi-Fi waves radiate out from where they're being broadcast from, roughly in a circular pattern. And when they hit objects, they can reflect and bounce off of those objects. As the objects pass through something as a solid object, they will attenuate, and it can also slow down the speed. So what happened, and this was just a horrible problem in the 802.11b and G days, was this thing called multipath. Basically, you've got one signal radiating out, and it's bouncing off of things in the environment. And by the time it gets over here to the other end, you've got the same signal coming in, but it's being sort of like echoes, right? So the direct stream gets there, and we'll exaggerate things. We'll say it gets here in 1 minute, and then the signal coming off here and bouncing off of this wall gets here. It takes a longer path. So it took maybe 1 minute and 2 seconds. This one hit this object and came over. This maybe take 1 minute and 1 second. So you've got basically the same signal coming in at different times, and it's like listening to an echo when you've got an echo bouncing off of multiple surfaces in an environment. And that caused confusion. And that was something we called multipath. So a lot of people smarter than me looked at this problem, and they first started coming out with ways with how do we ignore this multipath? How do we just focus on that main signal? Eventually, some people figured out that what you can do is you can take advantage of the slight timing offsets and actually send different data over different paths at the same time using the same channel. So it's allows you to increase the amount of data you can send at the same time. So this was something that we called MIMO, multiple in, multiple out. And you first started seeing this with 11N, and later technologies had the ability to do this. So basically, each antenna is able to broadcast using the same channel. So they'll both, so in this case, let's just look at the focus on these two antennas. So they'll both be able to use the same Wi-Fi channel. They'll be able to both use the full bandwidth of that channel. They'll transmit at the same time, and they'll take advantage of the multipath issues. And because these antennas are physically separate from each other, they physically will take different paths, and will send different data off of each antenna. So these are our streams. These are our spatial streams. So different streams of data following different spatial paths. So in this case here with 11N, the maximum speed that you can send is 150 megabits per second. Since we've got two different spatial streams, each spatial stream can carry 150 megabits per second of data that's separate from the other one. And then your client device can take those two streams and combine them together for 300 megabits. So this is your MIMO, multiple in, multiple out. And it requires multiple antennas on both the transmitting device and multiple antennas on the receiving device. Originally, when this came out in 11N days, the spacing had to be pretty significant. These days, spacing, it just has to be, I think less than a centimeter between your antennas to be able to take advantage of MIMO. So with 11AC Wave 2, they introduced a new technology called MU-MIMO, multi-user MIMO. uses the same thing, it uses the same spatial streams, same technology, but instead of sending 300 megabits to 150 megabit streams to one user, it sends two different 150 megabit streams, one to one user, one to another user. So this is MU-MIMO. So this way you can transmit data to two different users simultaneously, just that each one gets half the speed. So Jonathan's asking, so that's why more antennas equals increased speed. So yes, generally the more antennas you have on there, in general, the more spatial streams you have access to in general. And I'll get to that here with this very next slide. So when you're looking at data sheets, you will see spatial streams listed for anybody's business class product. You may not see it on consumer stuff, but business class products generally focus on the spatial streams. So basically you will see it being designated as something like 2x2 or 3x3 when you're looking at an access point. On client devices, you may see something different. You generally will see a smaller number as the first number and the second number as a larger number. So generally what this means is the first number is how many antennas can transmit at a time, and the other number is how many antennas can receive at the same time. So with APs, that's generally going to be the same. You're going to be able to transmit and receive the same number of antennas or same number of spatial streams at the same time. Client devices, your mobile devices, oftentimes it's easier to receive multiple streams and combine them together than it requires a lot more CPU power to then take your data, split it into multiple streams to send back to your access point. And so because of that, you will often see a device being able to receive more spatial streams than it can transmit back. And generally we don't care because generally you're downloading more data than you're uploading. Now there is one exception to this rule, which is primarily you see on Cisco data sheets. So on most vendors, you'll see 3x3, 2x2, 4x4. With Cisco, you'll see those same numbers, then you'll see a colon, and you will see a smaller number after that. So in this example here, you'll see 4x4 colon 3. So what's going on there? So what they're doing is they're saying, well, we've got 4 antennas. Each of those 4 antennas can be used to broadcast or receive data. However, the 3 is indicating how many of those can actually be used simultaneously. So in those scenarios, even though it says 4x4 colon 3, it's essentially a 3x3 device. You can actually only use 3 of those spatial streams. You've just got an extra antenna that you can choose to use versus a different antenna. So you can turn off, you can choose which 3 of those 4 you want to use based on the RF environment, essentially. So it's a little bit confusing. Realistically, from what I've seen out there, it's more of a marketing gimmick to make the number seem bigger. In theory, it gives you a little bit more flexibility on your antennas, so it maybe helps with reception a little bit, maybe. I'm not convinced. So to put it all together, you combine those three things together, and that's how you get the maximum speed of your device. So for instance, with 11N, with a single spatial stream, it had a maximum of 64 QAM, and with 11N, you have a maximum of 40 megahertz you can use. So that's why an 11N spatial stream is 150. So if you see a device that's advertising itself as N300, you know that that's using 2 spatial streams. And that's how they're getting to the N300. Obviously, it gets a little bit more complicated now when you've got 2 radios and you have to add the 2 radios together, but that's just showing you how it works. Now, again, at any point here, based on the quality of your connection, you may need to drop from 40 to 20. So essentially, you're halving your bandwidth. And you may not be able to use 64 QAM. If the signal to noise ratio isn't good enough, it may drop back to 16 QAM, dropping your speed even more. So when you're looking at a data sheet, it's basically taking the maximum. It's assuming maximum spatial streams the device can support, maximum modulation that the device can support, and the maximum free bandwidth that the device can support. So that's why when you look at 11AC products, you'll generally see like 900 given here. They'll round up these numbers. This will be rounded up to 450. This will be rounded up to 900, but that's based on 11AC wave 1. Is that right? No, 11AC wave 2, right? So you've got one spatial stream, 256 QAM, and you can use up to 160 megahertz channel. So that's where you'll get to the 900 that you'll see normally used in that. If you add a second spatial stream, you simply double that and takes us down here to 1733, et cetera. So that's where the speeds come from. And of course, the RF environment at any time can, drop down and drop the exact combination of these that you were using. So we get this question a lot, and it's unfortunately a question that does not have a good, clean, simple answer that I can provide you. And the question is, how many devices can I get on one AP? Most people go, well, it's an easy answer. I will look at the data sheet, and the data sheet will tell me how many devices I can connect to it. And unfortunately, that's wrong. So that number that you see on a data sheet is basically telling you how much memory is allocated to being able to manage association information. So in theory, that's how many devices could be handled by the access point. But in general, in the real world, you're going to start running into connectivity issues long before you get close to that number that's on the data sheet. So from a realistic perspective, there's really no difference between a device that says it supports 128 users and a device that supports 512 users. And the limitation here isn't on the access point, it isn't on the hardware, it's on the Wi-Fi technology itself and the limitations of the Wi-Fi implementation. Right, as we talked about before, except for when you're dealing with MIMO, each device has to take a turn broadcasting. So that's going to be a main component of determining how many users you can have on there before you have issues. It's going to have to do with, well, what sort of data are these transmitting, right? If they're just checking emails periodically, you can get a lot of users on there, won't be an issue. But if you've got users streaming video, it's going to be an issue because there's only so much airtime available before you just run out of available bandwidth that you can use. And then things like the technology, you have older clients and more powerful clients and newer clients all mixed together, so they're able to achieve different speeds and be able to use the available bandwidth more or less optimally. So that all affects things. You also run into issues, for instance, with latency and jitter. So if you're streaming video from Netflix, it uses a lot of bandwidth, but it's a lot more forgiving than something like voice over Wi-Fi, which is using a little teeny tiny amount of bandwidth, but is very sensitive to delays and jitter. So with Netflix, when you're watching a Netflix video, there is a buffer of a few seconds that allows it so packets that need to be retransmitted can be retransmitted. Packets can come in delayed, they can come in out of order, and then they all get combined together and played in the right thing due to the buffer. Well, voice communication doesn't like buffers, right? That's that delay between when you're talking to someone over like an old landline versus when you're talking to someone over a VoIP line. There's that very distinctive sort of delay, and you end up sometimes talking over each other, and then both stopping at the same time because everything's delayed a little bit. And if it was something like Netflix, it would be delayed a lot, but you have to keep that buffer minimal. And because you're keeping that the buffer so small, any sort of drop packets or delays in packets getting delivered can really degrade the performance. So you may run up in a situation where you can actually have more people streaming HD Netflix on an AP than you can have users simply using it for low bandwidth voice calls because of the jitter and packet loss issues that may come into effect there. So a lot plays into this. And we've got one example here for you guys of real world limitations. So in this case here, same thing, we've got users and they're watching what we'll call it a video stream here. So this stream of this video that you're watching is a 3 megabit stream. So we've got an access point that supports 3 spatial streams, and we start with a nice powerful laptop here that also supports 3 spatial streams. So with this combination here, we're able to get 34 laptops connected to that access point, all streaming this 3 megabit video stream, no issues whatsoever. Now, if we change the device to say a higher end tablet that only supports 2 spatial streams, the maximum number of users drops to just 21 because the two spatial streams are not, being able to take full advantage of the available airtime. So you've reduced your maximum speed. And so now you've gone from 100 megabits aggregated throughput to 65 megabits aggregated throughput. Only thing that has changed is what the client device you're using, how many spatial streams it supports. And then if you dropped it to, say, a lower end tablet that only supports one spatial stream, you're only going to be able to get 10 of them on that access point before you start running into issues. So that's just looking at spatial streams. And as we talked about, there's a lot of other factors that could also change, that may also increase or decrease the number of users you can fit on there. So there is no really easy answer for you. The main takeaway for you is don't use what's on the data sheets as a guide. It's not going to help you. Unless you're doing something where you've got a lot of devices connected that aren't sending a lot of data, maybe a smart home scenario or something like that, you're going to hit limitations of Wi-Fi itself before you get anywhere close to the maximum number of clients that you see listed on a data sheet. So now we're going to talk a little bit more about co-channel interference. So co-channel interference is just the industry term here for when two or more devices are broadcasting on the same frequency at the same time. And again, this could be two Wi-Fi devices, could be a Wi-Fi device and somebody's remote control car that also uses that same frequency. It could just be RF interference coming off of the air conditioner up on the roof, 2.4 signal, being used by your microwave to heat up your food, whatever it happens to be. Whenever you've got that interference, that's called co-channel interference. So one of the ways you deal with co-channel interference is you lower the output power of your devices. So right as we talked about before, Wi-Fi is two-way communication. And your access point generally can send that signal a lot farther than your client devices can. So if you reduce the signal or the signal strength coming out of your access point, you reduce the coverage area of that access point, but you also reduce the amount of overlap between it and its neighbors that might be using that same channel. Now, the downside of this is you are decreasing the amount of power output, so it will lessen your signal to noise ratio. So for those clients that are, fairly close to the AP, probably won't make any difference. For those guys that are sort of out at the edge of coverage area, it may make a big difference to them because the signal to noise ratio will shoot back up. Another way of dealing with co-channel interference is a technology we have on some of our access points called smart antenna. Very similar to Ruckus's BeamFlex Plus antenna technology. And basically what we do is instead of having a single antenna in there or a set of antennas with this fixed antenna pattern, we have the ability to use hundreds of different antenna patterns on the same access point. And it's able to choose in roughly real time the optimal antenna pattern that focuses the signal towards the client device. And our algorithm is also optimized to look for other sources of interference, regardless of what they may be, and choose an antenna pattern that allows the AP to kind of ignore and not listen to that noise that may interfere with it receiving the signal back from the client. So this smart antenna technology, it works with any client device. It doesn't require anything special technology-wise on the client device. And unlike beamforming, it works with mobile devices as well. So you can roam around and we're able to keep modifying the antenna pattern used for that client as they change and move in the environment. So I want to go through a sort of a case study here we did where we compared smart antenna to non-smart antenna. So in this case here, we took a Ubiquiti access point and we took one of our access point. Both of these are wall plate APs. Both of these are 11AC APs with 2x2. Both of them are roughly the same power output and receive sensitivity. So on paper, they're very similar products. The only difference between the Zyxel product and the Ubiquiti product really is we have smart antenna, they don't. So this is a hotel scenario where you've got one of these low-powered APs in each of your guest rooms. And we're using 5 gigahertz. We're using non-DFS channels. So we don't have any APs directly next to each other using the same channel. As you can see in the diagram here, we have two APs here on the same floor, and we have another AP on the other floor below them. And all we're doing here is we're going to start turning them on one by one, and then seeing what the aggregated throughput we can achieve on each is. So with one access point going here, roughly the same performance between us with smart antenna and Ubiquiti without smart antenna. In fact, Ubiquiti, not very minorly here, but they did nudge us out. They got 406 megabits per second as far as the aggregated throughput for their clients versus 404 on the Zyxel. And when it comes to channel efficiency, basically out of that available bandwidth that's available on that channel, both devices achieve 67% utilization of that airtime. So now next we do is we turn on a second access point on that same channel. Again, they're not right next to each other. There is rooms and floors differentiating them there. And we rerun the test. And this is now where you see the benefits of smart antenna. You will notice that our aggregated throughput for smart antenna APs jumped up to 785 megabits per second, whereas the Ubiquiti maxed out at 555. So that's like a 41% difference in aggregated throughput. You will also notice that the throughput for each AP is roughly the same. They're very close to each other, 385 for one, 404 on the other. When you look at the Ubiquiti, though, you will notice one of their APs is getting a lot more aggregated throughput than the other. We're getting 406 versus 221, almost a 50% difference between the two APs. And then if you look at airtime utilization, you see here Ubiquiti was able to get to 95% utilization. And we were able to achieve 31% over the maximum of 100. So 131% airtime utilization. And that has to do with the smart antenna and the ability of smart antenna to allow multiple devices to broadcast at the same time and not cause code channel interference. So because of that, we're actually able to use more than the theoretical maximum airtime. And then as we add a third AP and turn that on, we notice the same sort of behavior here. Aggregated throughput now is up to 900 megabits per second, whereas the Ubiquiti is still roughly in the 500s. You will also see again our distribution of the bandwidth is pretty equal between each of the different APs, whereas again on the Ubiquiti, it's really a mismatch of, some APs are getting a lot more than others are. And then if you look at the channel efficiency, we shot up to 155% channel utilization, where Ubiquiti actually dropped a little bit down to 91% because it's increasing the amount of retransmissions that are being required as you're getting interference between the different access points. So now let's talk about another technology we have that's called dual optimized antenna, and it's been designed to solve this problem here. And that is that most access points don't have smart antenna. They have a single fixed antenna pattern that's built into the access point. And that has been designed for you to mount this access point up on a ceiling, and it covers the area directly below it in roughly a circular pattern. Now, out in the real world, though, you don't always get to mount your APs on the ceiling. Sometimes you get to mount them on the wall. So when you do that, you have a less than optimal coverage pattern for your access point. It doesn't shoot out far enough from the wall, and a lot of the signal goes up into the ceiling and down into the floor where it may be absorbed, or it may pass through to cause interference on the other floor. So we have a technology called dual optimized antenna on some of our APs. So it has two different antenna patterns, one for the ceiling, one for wall, and you can switch between the two depending on where you've mounted that AP. So you can just buy one SKU and then mount it on ceilings where you can, mount it on walls where you can, and then be able to assign them and tell them which antennas to use based on where they've been mounted. So just a general rule here, most access points are designed for ceiling mounting. And in general, you want to mount them as high as possible within reason over the area to be covered. And the reason for that is you're trying to avoid obstructions, right? So you've got your ceiling here mounted, or your antenna, or your access point mounted on the ceiling. By keeping it up nice and high here, it allows the signal coming from this guy's computer to be able to go. Thank you, Alexa. It doesn't like me saying the word computer. It's the keyword on that one. So anyway, this way the signal is pretty much unobstructed going up to the access point, right? You don't want it to have to go through a person, a cubicle wall, a support beam, etc. So you're just trying to make it so it's got a clear path to the access point within reason. Now, obviously, if you're talking about a space like a SoFi Stadium, maybe it's not as good idea to put it up on the ceiling. It's too much space for you to get up there. It also may end up with the access point covering a much larger area than you want it to in those types of environments. So in general, a little tip here for you. So we have a lot of times we've had our resellers here complain that, my customer doesn't want me to drill holes through the drop ceiling to be able to mount the access point there, or maybe you're in an environment where they just don't want the access point to be visible. So in general, provided your local building codes allow it, those drop ceilings have very little attenuation. They're largely just cardboard, essentially. So you can simply set the access point face down on top of the drop ceiling to get your coverage pattern. So generally there's not going to be a lot of shaking going on, so it'll stay roughly in place. You don't have to poke any holes there. Again, provided your building codes allow it. We know that some places out there, they don't allow you to put stuff up in that place. So it's just there. If you are mounting to an actual ceiling, you need to take into account things like ductwork, lighting, other obstructions out there, right? And metal is bad for Wi-Fi signals. So you don't want it to be, your access point to be bordered on each side by conduit and some duct work for the air conditioning. Some lighting stuff, some ballasts for fluorescent lights can put out RF interference. So you generally don't want your access point right next to fluorescent light if you can avoid it, etc. So for hotels, generally the way that it had been done up until a few years ago was what we would call umbrella coverage. So with umbrella coverage, what you would do is you would mount access points in the hallway, and they would cover multiple rooms. Generally, we would say no more than 4 rooms. In the older days, when you had people weren't streaming Netflix, and it was probably just one guy in there with one laptop and maybe a phone on Wi-Fi. You would go up to maybe 8 rooms. In some cases where the floors were really thin, we've had VARs do one AP for 16 rooms in the old days. Unfortunately, that doesn't work too well these days because you've got a lot more users connecting to those access points. You've got a lot more bandwidth being utilized as people are streaming video and music. They're not just checking emails or browsing the web. You've got more Wi-Fi devices in each of those rooms. People may have a tablet, a phone, a smartwatch, and their laptop all connected to it. They may have their family with them, and each one of them have multiple devices. Then the other thing is, part of the ways that a lot of these cheaper phones and cheaper tablets get the price down is they use lower powered Wi-Fi, so they don't have as good of signal reception. So you run into issues where the Wi-Fi is out here in the hallway, and it's got to pass through. Oftentimes the bathroom is right up against that hallway. So you've got the signal's got to go through tile, it's got to go through pipes, it's got to go through another set of tile walls, and then across the room to wherever that user happens to be. So what we've seen is most of your mid-tier and higher hotels have switched to a per room or per every other room AP deployment where the APs are mounted in the rooms. So most vendors now, including us, have wall plate APs that are designed to mount onto a wall plate. The cable comes into the back of the AP, and then there's pass-through ports, including PoE ports. So you can run just one Cat5 or Cat6 cable to the room, use PoE to power the access point, use PoE to power something connected like an IP phone, and then you've got another cable running out to a set-top box that does IPTV. So this is what we're seeing in almost all newer builds, and we're seeing this be most hotels being upgraded to this in the mid-tier. You still see in some of the smaller franchise hotels, a lot of them still trying to do umbrella coverage. and just, deal with the trade-off that they're going to get more complaints about the Wi-Fi. Just some general things. If you're mounting APs into the guest room, guests will try to steal those. So ideally, you want to use a mounting bracket of some sort that's not obvious how to release the AP to remove it from the bracket. It may be a good idea to hide the AP behind some furniture, depending on what that furniture is made out of. And then another thing is generally you want to be able to turn off the LEDs on the access point, because people, they're trying to sleep, don't want to see a blinking or pulsing LED in their face. So some general things to keep in mind here, but this is definitely the way we see people going here with one AP per room or per every other room. It solves a lot of those issues that umbrella coverage gives us. Some other things here when it comes to hotels, when we're looking at public areas, basically what you're looking at is user density to determine how many APs you need. So a lot of times when people go in here and go, well, here's the measurements of where the area to be covered is, how many APs do we need to cover that area? I will say in hotels, you're looking more at the user density. How many users are going to be connected to that Wi-Fi network? Generally, that's going to determine how many APs you need, not the theoretical coverage area that each AP can handle. So basically, the more user dense an area is, the more APs you're going to want. You're going to want to use load balancing and client steering to help distribute those users across the APs in the area, so they're not all connected to the AP that's closest to them, overwhelming that one AP. And you want to provide different areas with their own coverage. So, treat the lobby separately from the pool area, treat that separate from the bar and the hotel restaurant, plan them each individually. And when it comes to like client steering and load balancing, you want to divvy up your network into areas that make sense. We've run into partners doing a hotel install, and they've basically set all APs to be able to do load balancing and client steering. So you've got, the AP in somebody's room on the third floor trying to push users onto an AP that's down in the bar on the other side of the hotel. So you don't want to do that. So you want to plan out and limit the groupings of APs that you're using for load balancing and client steering based on where they're located. And basically anywhere where you've got a high density of users or a high density of access points, use smart antenna. It's going to make your life so much better using smart antenna versus using traditional antennas. When it comes to schools, it's much of the same thing. How many students are going to be in that room connected to the AP? Is each student connecting to Wi-Fi? Is this a smart classroom or not a smart classroom? Well, all classrooms may have users in there with, a Chromebook or tablet provided by the school. A lot of classrooms don't use it. A English class may not be using any smart features, whereas another class, which is using a lot of videos and on-screen presentations, may do it. There's also different ways of implementing, how they're using the smart classroom. If you've got a teacher and they're using a smart chalkboard or whatever to display videos and to put their comments up, you're not going to need as much bandwidth as if you're in a classroom where the way the teacher shares things isn't broadcasting into a screen in front of the room, but they stream their desktop to each one of their students' computers. So you're now streaming video to 30 users. So it makes a big difference there. So learn a little bit about what that smart antenna is, and just in general, the more students or the more bandwidth intense the applications being used in that room, the more APs you're going to want. In general, though, for a room of up to around 20 students, we recommend for classes of about 20 students and up, 2 APs per classroom. If you have a room with 30 or more students in there, we highly recommend you go with an access point that has smart antenna. Our APs do have a special load balancing mode specifically designed for classrooms. And to handle the fact you may have 35 people, all connecting to the network at the same time and all disconnecting at the same time. So we've got a special algorithm that's designed to handle that. And I missed a question here. This is coming in from Jonathan. You may have more users by the pool than in a 2-room radius. You may want to have several APs by the pool at a lower power, right? Yeah, I wouldn't worry too much about the power. Generally, my experience is there isn't a lot of Wi-Fi demand by the pool. There may be a lot of users, but they aren't generally doing a lot with it. You know, if you're laying out by the pool, you're generally not streaming video. You're not doing things. You just have your device there, maybe for some web browsing. Maybe, or most likely, it's more like you're there and you just want to be able to get notifications if somebody calls you or somebody sends you a message. Generally, people by the pool are just lounging and taking in the sun or swimming, so they're not really using their devices. However, if you're in a situation where that's the opposite, you've got a lot of users, you know, hanging out in the cabanas and just watching video with their kids, then you may want to do more APs for that. Generally, you'd want to do outdoor, but yeah, I personally haven't encountered a lot of user dense applications around a pool area. Um, but obviously that can change based on the clientele and the class of hotel. Yeah, but yes, in general, the more users, the more stuff. So for instance, your lobby, depending on the type of hotel, you may only need 2 access points to cover your lobby. If it's primarily a lobby and doesn't have a big lounge area where you've got people eating and stuff, you know, it's in a separate area, you may get by with 2, whereas the conference room next door, you may need to have 4 APs in there. Even though it may be physically smaller than the lobby, you're having conferences where you're having, you know, 60 or 80 people crammed in there. So you would want to put more APs in those more dense environments. And again, in those really dense environments like that, you really probably want smart antenna as well. It does make a huge difference. So now let's talk a little bit about Wi-Fi 6 and Wi-Fi 6E. These are our latest technologies in the Wi-Fi space. So just to start with, Wi-Fi 6 and Wi-Fi 6E are the same thing. The only difference between Wi-Fi 6 and Wi-Fi 6E is able to use the 6 gigahertz spectrum. Wi-Fi 6 was designed from the ground up to implement the new changes across multiple different spectrums. It is not spectrum dependent like older Wi-Fi technologies are. So if you know tomorrow the FCC opened up a new chunk of spectrum, it should be very easy to port Wi-Fi 6 to it. It's more of just changing the hardware to be RF compatible with that new open spectrum. It didn't change anything else. It's just the ability to use that. And that's why there's such a small gap between Wi-Fi 6E and Wi-Fi 7. 6E is hitting the market because the FCC opened up the space rather than wait for Wi-Fi 7, which isn't ready. They wanted to get Wi-Fi 6 out there so people could take advantage of 6 gigahertz today. So, okay, so back to Wi-Fi 6. It was originally codenamed or called high efficiency Wi-Fi. It was 11AX was eventually renamed to just Wi-Fi 6 from a marketing perspective. So it was designed to work on all frequencies. And this is key because 11AC only works on 5 gigahertz radios. So if you've got a 11AC device, your 2.4 radio is still using Wi-Fi 4 or 11N technology. So Wi-Fi 6 does work across both radios, 2.4 and 5 and now 6. It was designed specifically to deal with a lot of these issues that we've been talking about up to this point, particularly in high density environments or environments where there's a lot of RF noise. So it's really good in environments where you've got a lot of users or you've got a lot of access points. There's a lot of things that go into it that make it better for that. And these technologies that they use are complementary to our smart antenna. So it's basically 2 different ways now of being able to handle those issues of density. You've got the tricks that Wi-Fi 6 does, and you can still use smart antenna and combine them together to get even better performance in those things. And some of the things that it's done here, as we talked about earlier, we've added 1024-bit QAM. We now support OFDMA, which allows us to chunk up the RF spectrum into much smaller and different sized allocations to better be able to handle multiple users at the same time. We now have the ability to support uplink MU-MIMO. So the ability for, before MU-MIMO was from the access point to the users, we now have the ability to have multiple users broadcast back to the AP at the same time. We have the ability to reuse frequency spectrum. We have being able to schedule when it's turn for different Wi-Fi devices to broadcast so they don't step on over each other's toes. This is the most significant change to Wi-Fi since its launch in 1997. A lot of improvements, but obviously to take advantage of these improvements, your clients also need to all be Wi-Fi 6 as well. So Wi-Fi 6 products have been on the market, I want to say, since 2019. However, the spec itself wasn't actually finally ratified until 2021. And so because of that, you will see a lot of products using older generations of chipsets don't support the full Wi-Fi 6 feature set. And because of that, the Wi-Fi Alliance for the longest time didn't require that you support all the features to get the Wi-Fi 6 Wi-Fi certification. They now have added most of those in, but the older products can still be Wi-Fi certified as being grandfathered in and not supporting some of that. So it's something you have to watch out for. So when you're looking at products, that's one thing to look out for. And unlike the 11AC where we had wave 1 and wave 2, or unlike 11N where we had pre-N and full N, everything's just calling itself Wi-Fi 6. The industry is not making it easy to tell what is a full Wi-Fi 6 feature set product and what is not. So you might want to look at data sheets, look to see if they support uplink MIMO, look if they support OFDMA. If they do, it's probably the newer generations of chips. In fact, I've got this here. So here's an example here looking at Gen 1 versus Gen 2 Qualcomm Wi-Fi 6 chipsets. Same or similar thing with Broadcom. You can see a number of the features are missing and cannot be added later. Some of these are very important. So when it comes to Zyxel, at least, all of our business class APs, so that's all of our NWA or WAX series APs that are at least 3 digits in the name. So NWA 110AX, NWA 220AX, et cetera. All of those support the full Wi-Fi 6 feature set. And we support it on both radios. And the reason I'm pointing out both radios is Ubiquiti and maybe some other vendors on their lower end Wi-Fi 6 products have only put Wi-Fi 6 on their 5 gigahertz radio. And again, you won't see that advertised. It'll just be, here's our Wi-Fi 6 AP. It won't be until you look at the data sheet and look at the speeds that you realize the speeds they're claiming for 2.4 are 11N speeds. They are not Wi-Fi 6 speeds, because in order to save costs and keep the price point down, they've left off some of those features. And in all fairness, we do have some lower end prosumer products, the NWA 50 and 90. They are missing some of those Wi-Fi 6 features, although it is still, Wi-Fi 6 Lite on both radios. We absolutely, all of our products, if they have any form of Wi-Fi 6, it's on both radios. Okay, so Wi-Fi 6E was something that just recently came along, and it was because of the FCC opening up a massive chunk of spectrum for us to use in the 6 gigahertz space. There is 2.5 times more capacity than with the previous spectrum we had available. And because of that, we can have 7, let's just go to the next slide. We can have 7 non-overlapping 160 megahertz channels. So right, for Wi-Fi 5, you had 2 and you had to use DFS. With 6 gigahertz, you've got 7, and you don't have to worry about something like DFS. Anything that's Wi-Fi 6E is Wi-Fi 6E and has access to all of this spectrum. As you can see here, 6 gigahertz is bigger than 2.4 and 5 gigahertz combined. And then you don't have to worry so much about interference because nobody else is using this chunk of spectrum. Indoors. So what are the concerns? Well, the problem is people have been using 6 gigahertz outdoors already. It's being used by news anchors to broadcast video and stuff back to their company. It's being used by utility companies for smart meters. And so for that, if you're going to be doing outdoor Wi-Fi 6E, there's going to be something called automatic frequency control that makes sure your APs don't interfere with these existing legacy users. Not an issue for indoors, but for outdoor use. And on top of that, the FCC is being sued by a bunch of people because of this. So because of that, there are still no outdoor Wi-Fi 6E products, and it may be quite some time until there are, because the FCC has not finalized the requirements for operating Wi-Fi 6E outdoors. And probably until those lawsuits are settled, isn't going to. So it was supposed to be out last year. No one knows now when that's going to happen. So for now, 6E is indoors only, and it is technically against the law to use 6E outdoors. Some other trade-offs, though, for using it indoors. Higher frequency again means less range. And if you check a lot of the 6E reviews out there, that is the problem. If your house you were already having issues with your 5 gigahertz router covering your entire house, you are going to have problems with your 6 gigahertz radio covering the house. It's going to be worse than your 5 gigahertz connection is. There are some lower power limits. So you can't, really crank up the volume or the power output like you could on 2.4 and 5. And then the other trade-offs are Wi-Fi 6E is going to cost more. So now in theory, you can have 3 radios operating 2.4, 5 gigahertz, and 6 gigahertz simultaneously. So you're going to need more power amplifiers, you're going to need more antennas, and you're going to need a beefier CPU to be able to process and handle all of that data simultaneously. In addition, you may need to update your other LAN infrastructure, right? You've got all this speed, in theory, up to 10 gigabits per second, just on the 6E radio. So you may need upgrade your network to multi-gig switches, depending on what generation that cat is that's in the wall. If it's the older Cat 5, you may need to upgrade that to 5E or 6 or 7. So those are the sort of the trade-offs of making the jump up to 6E. Now, we've gone to the negative. The positives here for us, right, is it's great for high density environments, provided you can get your clients to update their laptops and phones to 6 gigahertz. I believe all of the Apple products that have come out recently all support 6E. I know my Google Pixel phone, which is not the 7, which is out this year, it's the 6 Pro from 2 years ago. It supports 6 gigahertz, works just fine. So as long as your customers are willing to upgrade their other networking equipment, it's great for high density environments. And in the future, I assume something like CES or other big trade shows and conference spaces are probably going to really focus on 6E because, again, you've got 7 non-overlapping 160 megahertz channels. So it makes a lot of sense to try to use that in these spaces where you've got a lot of APs and a lot of users. And then just the high bandwidth makes it really good for high bandwidth applications. Another area where we see this coming into use is using 6 gigahertz for backhaul, right? So there's always been that promise of using mesh in businesses, and it's never quite been good enough for at least larger businesses to use. I know some smaller offices use mesh, but with 6 gigahertz backhaul and then being able to use your 2.4 and 5 gigahertz solely for talking to clients, and then 6 gigahertz for max speed backhaul, it starts opening up using mesh for deploying your APs in an office environment rather than needing to run Cat 5 to each of your APs and provide a wired backhaul. One thing I do want to talk about here, we're at the end, when it comes to Zyxel Wi-Fi 6E products, we've got 3 business class access points right now. The first 2, the NWA 220AX and the WAX 620, those are what we are calling here. Those only have dual radios. They do not have 3 radios. So one radio is dedicated to 2.4. The other radio is 5 gigahertz or 6 gigahertz. You choose which one. You can switch and choose which one you want to use. So that's been done to keep the cost down and to provide an affordable way to add 6 gigahertz support to an existing network where you don't want to replace all of the APs. You just want to add some in, maybe in areas where 6 gigahertz is beneficial for what you're doing, or just allowing you to deploy 2.4 and 5 today. And then in the future, when 6 gigahertz client devices are more common, you can always flip that switch and upgrade your network from 5 to 6 gigahertz in the future. And then our higher end product, the WAX 640, the 640 is tri-radio. So it has dedicated radios for 2.4, 5, and 6, and they all run simultaneously at the same time. And with that, guys, that is the end of today's webinar. Go ahead and send in any questions you have. I currently have none pending. Just as a highlight here, while I've still got you, most of our webinars are recorded and then uploaded to our YouTube page. There are many Zyxel YouTubes because we're a global company and each region has their own YouTube. So ours is called Zyxel America channel. That's where you'll find today's presentation recorded. You'll find past presentations. It's also where we post up video case studies, best practices guides, things like that, commercials. So check out our channel. And then we are on LinkedIn. Feel free to connect to us there where we are Zyxel US channel. Jonathan is asking when this will be posted. Generally, our webinars are posted within 24 to 36 hours of when we have them, sometimes a lot quicker, but 24 to 36 hours is a pretty good rule. So by tomorrow lunchtime, it'll probably be there if it's not there later this afternoon. I also do want to highlight here, we do have user forums, forum.zyxel.com. It is a place for you to talk to other Zyxel users. Unlike a lot of other vendors' forums, ours are monitored by our product management and our R&D teams. So even if they don't answer you, and sometimes they will, that's one of the areas where we keep an eye on to see what sort of feature enhancements and requests people are really interested in. So it helps us judge the priority on things. It's also where we post up generally security bulletins and release notes first. So it's a good idea to keep an eye on that for any security bulletins and things like that. That's generally where you're going to find them first. And with that, I don't have any more questions. I will stick around for just another minute, but I do want to thank everybody who turned out today. Be sure to check out our other webinars. Tuesdays are generally more technology oriented, best practices, more in-depth dives. Thursdays are generally more higher concept overviews, things like that, more of a salesy, markety type stuff. I do them, Tri does them. Marcus puts some on, and then I know some of our sales guys like to put on their own little trainings. I'm not seeing anybody else with questions, so I'm going to go ahead and end today's webinar. Thanks for joining me, everybody.